If you remember from 10.1, we talked about the difference between two proportions. 10.2 has the exact same premise, except now we're dealing with means instead of proportions. So let's talk about some important ideas about the sampling distribution for a difference of means. Let's talk about the shape first. The shape of any sampling distribution is always going to be approximately normal as long as the normal condition is met. So the ways to meet the normal condition are, it could be n1 and n2 greater than or equal to 30. You could have the populations normal, or you could draw a graph of each sample and the graphs show no outliers or skew. The center for a sampling distribution for a difference in means, mu of x bar 1 minus x bar 2 is going to just equal mu 1 minus mu 2. And when we start to do significance tests, that's going to end up being your null hypothesis, mu 1 minus mu 2, when we do significance tests. And the last thing is the variability of a sampling distribution. And the variability is the standard deviation of the difference between the two means. And that's going to be the square root of standard deviation 1 squared over n1 plus standard deviation 2 squared over n2. That's the sampling distribution, shape, center, and spread. And just as a reminder, the parameter of interest for a difference of means is going to be mu 1 minus mu 2. And the statistic we'll be using in this section for a difference between two means is x bar 1 minus x bar 2. So whenever we talk about a parameter, you should be thinking about the difference in the population means. And when we talk about a statistic, it's the difference in the sample means. Let's read this example and see how all of these ideas play in an example. So the heights of young men follow a normal distribution with a mean of 69.3 and a standard deviation of 2.8. Then the heights of young women follow a normal distribution with a mean of 64.5 and a standard deviation of 2.5. We take independent random samples of 16 men and 9 women and calculate the sample mean heights for both. What is the shape of the sampling distribution for the difference between the mean height of women and the mean height of men? And why is that the shape? So we're going to say it's approximately normal. And now we need to think about which of the three normal conditions we can use to justify this answer. Neither of the sample sizes is larger than 30. We don't have the individual data, so we can't graph it. So we have to rely on the fact that the paragraph told us that the populations are normal. So since the populations are normal. Now let's talk about the mean of the sampling distribution. So we're going to use the mean of the sampling distribution of x bar m minus x bar w is going to equal mu m minus mu w, which is given to us in the paragraph. 69.3 minus 64.5 equals 4.8. The last thing we want to do is find the standard deviation and interpret it. So let's calculate it first. The standard deviation of x bar men minus x bar women is going to be standard deviation men squared over n men plus standard deviation of women squared over n women. So if we plug in those numbers, we've got 2.8 squared over 16 plus 2.5 squared over 9. And when you type that into your calculator, you get 1.088. And we want to interpret this standard deviation as well. The main idea of standard deviation is it's the average distance from the center. So if we put this in context of the problem, you would say the difference in the sample means is typically varies from the center by 1.088. And if I put that in context, the difference in sample means x bar m minus x bar women typically varies from 4.8, which was the center, by 1.088. We can use our knowledge about sampling distributions for a difference in means to create a confidence interval. So we know that the generic formula for a confidence interval is statistic plus or minus critical value times the standard deviation of the statistic, which is often referred to as the standard error. So if you see that, that's what they mean. The standard error is just a fancy way of saying that we're using sample data in our standard deviation instead of population data. And that happens a lot with confidence intervals because the whole point of a confidence interval is to use sample data to estimate the population. It's completely backwards from most of our other inference things that we do, like significance tests. So the generic formula is statistic plus or minus critical value times the standard deviation of the statistic. And we talked about a little bit earlier in the video how the statistic for a difference in means is x bar 1 minus x bar 2 plus or minus the critical value. The critical value we use for means is t star. And the standard deviation of the statistic, instead of using our population standard deviation in this formula, we're going to have to use the sample standard deviation. So S1 squared over N1 plus S2 squared over N2. And if you remember, T star is obtained by doing inverse T, the left area depending on your confidence level, and degrees of freedom. Normally, degrees of freedom is n minus 1, but now we have two sample sizes. So to get the degrees of freedom for two samples, you would do the smaller or more conservative n minus 1 to get your degrees of freedom. And your left area depends on the confidence level. And you'll see how that comes into play in this example that we're about to do. Confidence level here. So let's take a look at this example. Mr. Wilcox's class performed an experiment to investigate whether or not drinking a caffeinated beverage would increase the pulse rates. So 20 students in the class volunteered to take part in the experiment. So we had volunteers. That's going to be important later. All of the students measured their initial pulse rate in beats per minute, and then Mr. Wilcox randomly assigned the students into two groups of 10. So random assignment came into play. That's going to be important when we do our conditions. The students in the first group drank 12 ounces of caffeine, and each student in the second group drank 12 ounces of caffeine-free soda. All the students measured their pulse rates again. So what they recorded was the change in their pulse rate from drinking caffeine or not drinking caffeine. The first thing I noticed about this data is they give me a mean, but they don't give me a standard deviation. So what I'm going to do is I'm going to type all the caffeine data into list 1 into my calculator and all the no caffeine into list 2 of my calculator. Then I'm going to do one variable stats in my calculator to get the standard deviation for list 1. So 1 var stats list 1 will give me the standard deviation for list 1. And 1 var stats list 2 is going to give me the standard deviation for list 2. And if you remember, the way you get to 1 var stats, one variable stats, is you click the stat button, arrow over to calc, and it's the first option. So when you do that in your calculator, you get the first standard deviation to be 2.70 and the second standard deviation to be 2.62. So we're going to do a state plan do conclude problem to construct and interpret a 95% confidence interval for the difference in true mean change in pulse rate for subjects like the ones who drink caffeine versus those who drink no caffeine. Let's state all of our given information. We know that x bar 1 is 3.2, x bar 2 is 2.0, S1 is 2.70, and S2 is 2.62. We are only using subscripts at this point, so we need to define a variable. So I'm going to state our parameter of interest. We're trying to estimate mu1 minus mu2. We're trying to use sample data to estimate the true mean. So that's the true mean difference, or the true difference in the means, in mean pulse rate for caffeinated minus non-caffeinated. So we want to define the variable somewhere in there so they know which one's mu1, which one's mu2, which one's x bar 1, which one's x bar 2. So we're going to define that variable there. We're also given a confidence level of 95%, and we know that both of our sample sizes are 10. So that's all the given information that we have. Now we're going to do the conditions. This was not a random sample, but it was an experiment. When you have an experiment, the individuals are automatically independent, so you can ignore the independent condition. But usually with experiments, you cannot have random selection, especially if it's some sort of medical study. So random assignment is good enough for the random condition, if you can't have a simple random sample. So it's an experiment, so there was random assignment. That will meet the random condition. We need to meet the normal condition, though. We can ignore independent because it's an experiment, but we need to show that they're normal and n is less than 30, and they don't tell us the populations are normal, so we're going to have to draw a graph. So I'm going to do that over here. It's just going to be a quick dot plot. The smallest number is -2, and the largest number looks like it's 8. So we can just draw a quick dot plot here. Alright, so here are my dot plots. The dots going up represent x bar 1, and the dots going down represent the data for x bar 2. So neither of them have any outliers or strong skew, so that'll be good enough for me. The graphs have no strong skew or outliers. No strong skew or outliers. And then we ignore independent condition because experiment. And you don't have to write this part, I'm just writing it so that we can reinforce this concept. You ignore the independent condition because it is an experiment. Alright, so we've got all of our information stated. We have met the condition, so now we can actually start constructing our confidence interval. So we know we're going to have statistic plus or minus critical value times the standard error. Our statistic is x bar 1 minus x bar 2 plus or minus t star times the standard error, s1 squared over n1 plus s2 squared over n2. And we have x bar 1, x bar 2, s1 and s2, n1 and n2, but we don't have t star, so we're going to have to get a t star here. It's a 95% confidence interval, which means you've got 2.5% on either side. So to get our t star, we're going to do inverse t, 0.025, and then degrees of freedom are 9, n minus 1. And when you do that, you end up with a t star of 2.26. So now we can plug in all of our data here. We've got 3.2 minus 2.0 plus or minus 2.26 times the square root of 2.7 squared over 10 plus 2.62 squared over 10. And you can type this into the calculator in many steps. You can get the standard deviation as a decimal. You can simplify the means. But just be very careful with how you're typing this into the calculator. Practice typing this into the calculator right now and see if you get the same answer as me. -1.491 to 3.891. And just like the last section, you're allowed to get negative numbers. That just means that the second mean was bigger than the first mean if you get negative numbers. The last thing we need to do is conclude. We are 95% confident that the interval negative 1.491 to 3.891 captures the true difference in the mean change of pulse rate. It's helpful if you use the same wording as given to you in the question. So up here they use for the find the confidence interval for the difference in true mean change in pulse rate for subject like those. You could just rewrite everything I highlighted as your conclude. So that is confidence intervals for a difference of means.